Thanks, Jack, for the introduction. So today I would like to talk about the new features and algos that we added since last H2O World. Last H2O World was in December, so that's almost half a year, and it's good to recap what we did in that time period. Oh, it doesn't go forward. Yeah, it doesn't do anything. Anyway, so the good news is that everything I will be talking about is available in the latest H2O release that's available on our website. Yeah, and that's the. Can we go back? Yes. To the next slide. Yes. Perfect. Thank you. So, yeah. So everything is available in the latest release that we released just yesterday. And today we found out that you should probably not use Java 7 with this release. And the reason is that we apparently added too many features and the code base grew too much. And Java 7 has a bug that prevents you from loading the H2O jar and using it. So definitely use later version. But I was really bummed out about it this morning when I found out that it doesn't work on the older version of Java. But in a way, it's a good thing. We added too many features, and old Java cannot handle it anymore. So that's a good. That's at least the positive view. Anyway, we will fix this issue in a further fix release. But for now, please use Java 8. Yeah, it just takes a little bit to switch the slide. So let's dive in the features that are coming in H2O 3.20. The major addition is a completely new algorithm, Cox Proportional Hazards Model, or Cox-PH. And this is a model for survival analysis. It models association between survival time of, let's say, patients and one or more predictor variables, but it has applications in healthcare, but also in other fields. You can use it for churn analysis. I will not go into details for this algo because in the second half, Patrick will be talking about it in detail. We greatly improved our implementation or integration of XGBoost. We added ordinal regression to GLM. We did many smaller algo improvements, and I will mention some of them. And we improved the rest of the platform as well. We added new ways of managing data, and ways of ingesting data. Let's talk about distributed XGBoost. This is not a new addition in the latest release. This is something that's available since February. But if you are familiar with the first version that was released in February and you tried the current implementation, you would see that our current implementation is greatly improved, and both in multi-node and single node. It is much faster, especially in the single node. That's the most apparent, and you can see it will be 8 to 10 times faster, and we are getting comparable with the speed of the native XGBoost. We will always have a little bit of disadvantage because we need to move data from Java to off-heap memory, but we are working on improving that as well. The implementation is also less memory hungry, and especially on datasets with many categorical columns or high cardinality categorical columns, you will see that it will require much less memory, and it will be really apparent. We also worked on increasing stability of the implementation. We were adding many tests. We were stress testing the implementation. We added performance tests. So you should again see that the stability is greatly increased and much more usable than the first version that was available in February. We know that our enterprise customers care about easiness of deployment, and we added a new feature to our Mojo deployment story. Right now, you can enable Java-only scoring. You don't need to score using the native code that comes with XGBoost, but you can just score with Java-only code, and it enables you to use or predict. It enables you to predict also on Windows or other unsupported platforms, but you can enable it in any deployment scenario if you don't want, for whatever reason, the native code to run. We are not done with the improvements yet. We have a long roadmap what we want to do. The first thing what we want to do is to use the Java scoring also in training, and that will further improve the performance. We want to sync up our version with the version used in H2O for GPUs so that you get a unified experience across our products, and we want to integrate it in AutoML, but I will mention that later. Next notable addition is addition of ordinal regression in GLM. Ordinal regression is a way of ranking learning, and basically you want to do a regression analysis to predict an ordinal variable. Ordering of the variables matters. You can use an example of users giving ratings to movies. You can pick from 1 to 5 stars, and obviously it's a worse misprediction if you predict 1 star, or if the actual is 5 stars, and if you predict 4 stars. This is used in social sciences, and it's available in in GLM. The only thing you need to do is to set the family parameter to ordinal. We didn't just implement the standard version that you might find in R, but we implemented a custom version that provides better accuracy. We are working on improving the existing algos as well. In December last year, we were working on improving reproducibility of GBM or the tree models in multi-node clusters. So now we can say that our GBM and DRF is 100% reproducible. We added support for quasi-binomial distribution. We are always improving Mojo and exposing new functions in Mojo to give you more insight what the Mojo is doing. So the latest addition is addition of leaf node assignment. In GLM, we added a new parameter that lets you specify interaction pairs. So you can specify exactly the second-order interactions you want to explore in GLM. In PCA, some versions of PCA or some parameterizations of PCA depend on single value decomposition, and we added new backends for calculating SVD, and that's again resulting in better performance. In GLRM, we added support for missing data imputation, and similar to the output of autoencoder, you can optionally also get the reconstructed row on the output. We are making improvements in the general platform that's running the algos. One of the improvements is better rebalancing of the H2O frames before the actual model training happens. Sometimes when you heavily preprocess the data, you can get uneven distribution of the data across the whole cluster. Or if you are working with binary files that are heavily compressed, you can again get uneven distribution. So we improved the rebalancing logic, and this helps to utilize the cluster better. One small thing that we improved is actually calculation of AUC, and it's surprising that such a small thing can provide a significant increase of performance on some data sets. So the example says that on a Higgs data set with just 50 trees, just because of the AUC speed up, you see 25% faster overall training. So that was surprising to me that we can change one more small thing and we can get really significant performance improvement. We also improved how the gen model jar looks like. That's the thing you put in your production. And we made sure we don't bundle any libraries that are not absolutely necessary. And hopefully, this way, it will not prevent you from any complex deployment scenarios where you might be clashing with any libraries that we use inside. Further, from the platform improvements, we improved our parser. The CSV parser better supports text data. We added new features to data munging. In R, we exposed target encoding, and we implemented both leaf-one-out and cross-validation target encoding, which is good for categorical predictors with high cardinality especially. This is now exposed only in R, but we have planned to add it to the Java backend as well in future releases. The group by function now accepts rank, so you can do ranks in groups. And we implemented the expression optimizer, so when you are doing a complex script where there are for loops over complex expression, then we are able to optimize what's going on the back end and do it a little bit smarter way, and it, again, should increase the performance. We have integration with Google Cloud Storage. In similar way, we are integrated with AWS S3, and we added new data sources for our JDBC ingest interface. We have now support for IBM Netezza, and experimentally, we also added support for Hive 2. Now I would like to talk about the future releases, and we want to focus more and more on AutoML. As I said, we want to integrate XGBoost, and the integration should be as an independent algo in the stack of models that we are building, but we also enable it. We want to also enable it as a meta learner. We want to let you do a grid search over the meta learner parameters in stacked ensembles. Sorry. And we also want to expose the target encoding and possibly use it in AutoML, and that should provide some performance in terms of accuracy boost. We already started working on a new algo, isolation forest. That's a algorithm unsupervised for anomaly detection. And the typical use case would be, for example, fraud detection. We have plans for post 3.22 release. We have a long-term goal of adding factorization machines, because that would nicely complement the existing algos and enable you to implement recommender systems with H2O. And we want to add some more stuff for NLP, TF-IDF, and eventually also lets you define a custom loss function for GBM and DRF. At this point, I will hand it to Patrick. And he will talk about ClockPH.
Thanks, Michal. And are we queued up for the second presentation? I can wait a second. So as Michal mentioned, one of the major algorithms that's been released in the latest version of H2O is Cock proportional hazards modeling. It's an older technique. It dates back to 1972. And okay, it's not up yet. And it's geared towards analyzing time to event data. So if you've done a lot of, okay, great. If you've done a lot of logistic regression modeling, sometimes that type of data is conducive to this type of analysis, because what the intent behind the algo is to say, given that an event hasn't happened, what's the chance it's going to happen in the next time instance? So the idea behind this is that rather than blocking off big chunks of time and saying what's the chance that something's going to happen in that big chunk of time, you're looking at more incremental behavior. And just like logistic regression modeling, it looks at the way that the feature set contributes in a linear manner. So this has a lot of linear features in it. Obviously, you can derive nonlinear features from linear features, but the onus is on you to do it. the name hazard comes from the hazard function. So Cox proportional hazards is that you have this underlying baseline hazard that's applicable to either everyone in the population or to subgroups of the population, and those subgroups are called stratum. And the hazard function is just what's the instantaneous rate at which the event will happen in the next time instant. Now, obviously, you're not necessarily looking at data, in the next millisecond, but what you might do is look at it for specific time periods. So as I mentioned, you have a baseline hazard function represented here by that lambda function, and then you have this linear combination of terms that you're going to try to estimate using the Cox-PH procedure. When you're looking at this, you tend to want to know what's the chance of either the event happening up to a point or the chance that that the event hasn't happened. And if the event hasn't happened, that's the survival function. And a lot of this started out looking at, as the name suggests, whether or not something lives or dies. And so a lot of the terminology comes about from that. But this could be, the types of events could be what's the chance that somebody makes a claim on an insurance policy, or what's the chance that somebody makes a purchase if you're selling goods. So what it is that you're modeling doesn't have to relate to biological type data, but one of the key pieces to the Cox proportional hazards function is the two pieces are whether or not the terms contribute to the model in a linear fashion, and also how well the proportional hazards assumption fits to your data. In terms of the big data component is, where, just like with logistic regression, when big data really kicks in is if you're looking at something that doesn't occur all that often, but it might have a big impact on your business. So as I said, in the insurance claim business, hopefully the claims don't come too often, but when they do come, there's a big payout associated with them. And so you want to make sure that these rare events that have big business importance are properly modeled. And in order to properly model them, you tend to need lots of observations in which to do so. Another piece of this is that when you're modeling this time to event data, it's not just the event that changes for an individual, it's the characteristics of the individual. So, for example, an individual might become unemployed during the monitoring, and so you have something called a time-dependent covariate in which the covariates of the feature set could change over time as well. And that actually can multiply out your data set, because for every time a characteristic of an individual changes, you're going to now have another record of data in which to analyze, and so that can really grow out your data set. So having the ability to analyze lots of data, for rare events that have a big impact on your business, or if you have characteristics in your data that are changing along the way as you're waiting to see whether or not the event can occur, these things need to be taken into account, and you need to make sure that you can analyze it. So this is where H2O comes in, and it's Cox proportional hazards, a modeling algorithm. I'm just comparing this against one of the gold standards in Cox-PH is the survival package by Terry Thurneau out in R. Another gold standard one is Proc-PH Reg and SAS. So those are kind of the two most commonly used algos. So I'm comparing here, the orange line represents how Cox-PH behaves as the data set grows relative to H2O. And here I'm just looking at it on a modest sized machine in AWS using H2O. And you could see here that you have a nice linear behavior as the number of rows grows over time. The amount of time it takes to analyze goes along with it. For Cox PH, you know, for this software, eventually you're not even going to be able to analyze the data, and so that's why you see that the last piece of the puzzle here is missing, because it actually couldn't analyze those large data sets. So the behavior that one would expect out of H2O holds true for Cox proportional hazards model. The function looks like this. The main pieces are the specification of the data. Now, unlike logistic regression, where you just have an outcome or target variable, here you have a combination of things, is whether or not the outcome has happened, you know, yes or no, but also specifications of time. And so you have a start time and a stop time. And if you have time-dependent covariance, you can have multiple start-stops, because as the characteristics of the individual change, you've now you know, stopped it at one point and started it at another point. So that's the specification of the data. Another piece is a big part of the Cox proportional hazards model as function, as I mentioned, is the proportional hazards assumption. And in order to deal with that, sometimes what you do is to use stratification variables, and you can specify one or more stratification variables. And then the last piece is the interaction effects. So while you know, the nonlinear effects are kind of on you in order to add to the model, you could specify the interaction effects using some of these parameters. And as Michal has mentioned, a new parameter that's been added to the family of parameters is the interaction pairs. And then the last thing I wanted to just mention is the functions that are also associated with this. Now, currently this is an R-only implementation. Well, R interface only usage, I should say. The back end is still all happening using our high-performance Java in the H2O cluster, but we just have an R interface. There are a couple of functions that you can use to extract components of the model. You have the coefficients, just like you would have in a generalized linear model. There's also some model summary statistics as well you can grab. And in this case here, we have two types of scoring functions. One is the linear combination of terms, which is something similar to what you'd get out of a GLM. And you can get at that information using H2O predict. The other one is getting a survival curve. And I had an example, but in the interest of time, I'm not going to be able to show it. But what you could do is you can actually see how the likelihood of the event occurring over time is what's going to happen is, well, the likelihood of the event not occurring over time, I guess I should say, so survival. You're going to see that you can actually plot over the time domain that's of interest to you the likelihood that the event doesn't happen, and you can grab that curve using the survfit function. So those are the two scoring functions you can use. And for those of you who have used the survival package in R, these functions should seem very familiar to you. That's on purpose. We try to make familiar interfaces to the native language that you're operating in. So do try them out. Yeah, so just as a sales pitch, for those of you who do use H2O and have fit Cox proportional models in the past, I encourage you all to use this. For those of you who have used logistic regression a lot, I'd like for you to maybe just think about your problem a little to see maybe a reformulation of it might be better, because you can have a finer tuned understanding of when an event occurs. So please do try these out. Thank you all for coming to H2O World, and I appreciate your being here. I know that we've been running late, and so yeah, thank you.
Thanks, Patrick. Okay. I think we're ready for our next presenters.